Welcome. Today I want to talk a little bit about how semiconductors that we've been discussing in the previous few sessions interact with electromagnetic radiation, which we discussed in the last session. So let's get started. And basically, I want to retake a little bit where we stopped 2 lectures ago. In the sense that we introduced what a diode is and so on, and what are the levels of the materials and how the band structures look like and so on. So the first thing that I want to tell you about is I want to ask you a question, and very quickly, just for the sake of it, it's good to have a rough idea of what is the order of magnitude of certain quantities. And the question is how much momentum is carried by a photon. And the answer is relatively simple. The momentum of a photon, is going to be given by h divided by lambda. And just to put a number, let's say we use 800 nanometers. That's in the edge between the infrared and the visible region. So it's a deep red, or it's nearly infrared already. And the values that we have to put in here is 6.6 times 10 to the 34, to the minus 34. And divided by 800 nanometers, which is 800 times 10 to the minus 9. Okay, and if you solve that, the answer is about 8 times 10 to the minus 28 kilograms meters per second. Okay, now let's see how much momentum does an electron have in a material, let's say in a semiconductor. And there are various ways of estimating that. One can use the edges of the Breuer and so on and so on. I will do something a bit more simple, just to have a feeling that, again, I just want to know the order of magnitude, how much momentum is carried by an electron in a material. So the first, and using just classical approximation. So the first approximation, the momentum of an electron is given by the square root of 2me. This is the same equation that we've already been using. The energy is p squared divided by 2m. And again, the amount of energy that an electron has typically in a material at, let's say, room temperature, the energy is typically proportional to kT. It could be 3/2 of kT, depending on the degrees of freedom and so on. Let's just say kT. Again, we're just looking for a rough approximation. So approximately square root of 2m kT, where K is Boltzmann constant and T is the temperature. So if we put some numbers in, this is equal to square root of 2 times 9.1 times 10 to the 31 minus 31, which is the mass of the electron, and times 1.4 times 10 to the minus 23, which is Boltzmann's constant, times 300 Kelvin, which is the room temperature, roughly. And this gives approximately 8.7 times 10 to the minus 26 kilograms meters per second. Okay, right. What does this tell us? So what we can see is, if you look at the exponents of these, they're actually very different numbers. They differ by a factor of 100 or so. So a photon has roughly 1/100th of the momentum that an electron has. And that's to be expected. I mean, a photon has momentum just because of these quantum mechanical properties, but it's actually a massless particle, while the electron does have a mass. So this is somehow not entirely surprising. And this is important because there are a few aspects or a few more details about the band structure of semiconductors, which we haven't discussed. I mean, so far we have mentioned that we approximate the band structure as a parabola. This is not true in general. Actually, for real materials, they could be parabolic in certain regions, or their parabolic approximation could be good in certain circumstances. But the majority of, all real materials actually have a more complicated band structure, which has a complicated shape. And one of the things that happens is that not always, I mean, we've always put the minimum of the conduction band and the maximum of the valence band aligned with each other. So if in this direction we're putting the k vector, we have usually put these 2 points aligned with each other, but there's actually no reason to do that. So there are many cases in which the minimum of the conduction band and the maximum of the valence band are actually not aligned with each other. So this appears these two appear in different places. Well, and this changes things substantially. Examples of materials like the one we're seeing on our left-hand side of the screen are, for example, gallium arsenide, or indium phosphide, or several other materials that so happen to be, I mean, one can make many semiconductors by combining atoms of the 3 and 5 groups. So if you remember, these more or less make sense if materials like silicon or germanium are that form semiconductors are materials in the group number 4 of the periodic table. If instead of using all atoms from the exact same group, or just putting silicon, or just germanium, or just carbon, for example, which also forms different crystals that have semiconducting properties, one could use a combination in more or less, let's say, in equal amounts from group 3 and group 5 materials. And this means that some of them will have one additional electron, and the other ones will have one too few, and more or less things compensate, and one would at least intuitively expect that a group 3 atom plus a group 5 atom will produce a semiconductor. And this is true, actually. There is a whole family of materials that have been made combining atoms from the group 3 and group 5, and they are called in general 3-5 semiconductors. In general, many 3-5 semiconductors fall in this scheme, where the minimum of the conduction band and the maximum of the valence band actually line up with each other really nicely in k-space. But many other materials, and here this is not entirely expected, at least I wouldn't expect you to expect this, but silicon, for example, silicon is actually of the other type. The minimum of the conduction band and the maximum of the valence band do not align with each other. Germanium is another case. These are both group 4 semiconductors. And there are essentially two types, and we call these ones, the ones on this side, direct. Bandgap. Semiconductors. And we call the other ones indirect. Bandgap. Semiconductors. Okay? And this actually changes things quite a bit in terms of the way these materials interact with electromagnetic radiation. And it also changes things in terms of what kinds of optoelectronic devices can be made with the two types of semiconductors. So at first glance, this would not look like something that makes a big difference. Although, yeah, intuitively we have thought of the scheme more in terms of the diagram on the left. So we've always thought of direct bandgap semiconductors, but the truth is both of them exist, and they both have. I mean, everything that we have said so far is true for both kinds. So all the electrical properties really do not change dramatically. I mean, they do change in terms of the precise form of the band structure. But the fact that the two bands are aligned in K-space or not does not necessarily change everything we've said so far about the semiconductors. So let me draw here again a band structure of a direct bandgap material. So this is this is not actually very well aligned. So let me draw it again. So let's think of a material that has the minimum of the conduction band and the maximum of the valence band aligned with each other. And let's now think in terms of optical transitions. So let's say we send a photon in. So I will represent these by an arrow here. This is a photon coming in, and let's think in terms of an intrinsic semiconductor. So it has a completely populated valence band, a completely empty conduction band. And so there are electrons all over here, so all these states are populated. And when the electron arrives, if the electron, let's say it's a short wavelength, the photon arrives, if it's a relatively short wavelength, it has enough energy to produce a transition between the bands. So the minimum energy we would need definitely in order to produce a transition between the bands is producing a transition between this top state and this bottom state between the valence and the conduction band. This is more or less clear. So if the photon has this amount of energy, it can in principle produce a transition between these two states. But if the photon has more than that energy, let's say it has 10 or 20% more, the question is what happens if it hits this same electron? Let me erase that just for a second. Let's just patch this up a little bit. And if the photon has too much energy, what happens is this electron over here will want to have, I don't know, let's say this amount of energy. And it so happens that there is no available state there. So something that one could in principle think, okay, we have to conserve energy, so this electron could maybe promote to this state over here and occupy that state. However, this transition cannot happen. This transition cannot happen. And this transition cannot also not happen. This one over here cannot happen just because there is no state that has this combination of K and energy. And this transition cannot occur, this one over here cannot happen, because if you think in terms of the momentum of the electron will have to change a fair bit. So this electron will have to acquire all this momentum in order to have this transition. And it so happens, as we said in the previous slide, that photons don't carry very much momentum with them. So if there is no conservation of momentum, this transition can actually not happen. Therefore, the only transitions that can happen in this context are transitions that happen vertically. So this means that the electron will start and finish with a state that has the same momentum. Okay, it can change a little bit, but we're talking about 1% or maybe even under 1%. So for every practical purpose, all optically mediated transitions between one band and the other will have to be vertical transitions. So, for example, this transition from this state here, this electron over here, to this state over here, that one is actually allowed. This one is allowed. So, yay! This is good, right? If the photon has even more energy, maybe it can promote this electron over here into this state over here. But the thing is, these transitions, all optically related transitions, so the transitions that involve the absorption or emission of a photon, have to be vertical in this band structure. And this is something that changes dramatically from other types of transitions. There could be other forms of transition that maybe involve a mechanism in which momentum can be gained or lost, and then diagonal transitions can, in principle, happen, but definitely not transitions that involve just the emission or the absorption of photons. Exactly the same apply to the emission of a photon. So if this transition that I just drew here happened not just by the absorption of a photon, but more like for if the populated state was this one, and this electron wanted to get rid of the energy, this transition would have to be vertical as well. So the electron cannot recombine to this state over here or to this state over here. It has to be to a state that is vertically aligned with it in K-space. Right, so now let's think of a band structure that is not aligned. So here I will draw now another band structure in which the minimum of the conduction band and the maximum of the valence band are not aligned with each other. And the question is, what will happen in this case? Well, for the same arguments that we gave, a transition from, let's say, this point to this point, from this point to this point, is not allowed. Okay, this cannot happen. We know that transitions have to be vertical, so optically mediated transitions. So either the absorption, for example, the absorption of a photon that comes in will have to produce a transition from this state over to this state. That is a transition that is allowed. Or the recombination, for example, can happen from here to here in principle, but diagonal transitions cannot happen, at least not when they are mediated by photons, by the emission or absorption of a photon. So this changes things a bit. Now things start looking a little bit different. And let me draw the indirect bandgap band structure again in here. So let's think this is the conduction band, the valence band. They're not aligned with each other in K-space. And let's say that now we have just one electron over here. All the rest of the states in the conduction band are free. And let's assume that we have, for example, a hole that is occupying exactly these the vertically aligned state. And let's assume that the rest of the band of the conduction, of the valence band is occupied. So the question is, what will happen now? Will these, for example, these electrons try to recombine with the hole? In principle, that's allowed, at least by energy and momentum conservation. That is something that can happen. There is no reason why this process is forbidden. The only thing is, the question is, how likely is it to happen? And here the answer is, it's actually a very unlikely process. Because, first of all, the hole will try to lose its energy, its excess energy, by making transitions to the neighboring states. And this electron will also try to reduce its energy by going down the ladder into the valley. So essentially, all transitions, both these transitions that I put here in red, which are thermally mediated, and we haven't spoken too much about phonons, which we will cover in the next lecture, but basically these the electron and the hole here have two choices: either to produce a recombination between the two of them by emitting a photon with a lot of energy, or they can give their excess energy, their momentum and excess energy, so reduce their energy by giving this energy to the lattice and producing vibrations in the lattice, so basically producing heat. Increasing the temperature of the lattice. And this is what these red arrows mean. So the two possibilities are available, and the question is, which one is more likely? And here I will not go into the details of the arguments of why, but the thermal transitions are far more likely. So as soon as one of the two starts moving away, so that the two K vectors are no longer aligned, the optically mediated, so the photon transition is no longer available. This is no longer a possibility. So what will happen in most cases, again, this is, I'm saying, maybe one of every 1,000 cases like this will end up in the emission of a photon. But in most cases, what will happen is the thermalization of the carriers. So the carriers will try to move to the minimum of their band. So in the great majority of the occasions, what we will end up with is a band that looks like this. Just one hole here, all these states populated with electrons, and just one electron in the minimum of the band. And then there could be other mechanisms that allow these electrons to go down to the conduction band, but definitely not optically mediated mechanisms. So these ones will definitely never happen. And that's just because of momentum conservation arguments. So in this sense, the properties of the optical properties of direct and indirect bandgap semiconductors are very different. And they are very different, especially in the sense of the recombination. So transitions from the conduction band to the valence band that imply the emission of photons are extremely unlikely in indirect bandgap semiconductors, while for direct bandgap semiconductors we have the opposite case. However, the absorption properties is a different story. I mean, if a photon has enough energy to produce a transition between two bands, I will draw another indirect bandgap band structure over here. If the photons have enough energy to produce transitions up, as long as they are vertical, all of these transitions are allowed. and they not just allowed, they are quite likely to happen. What is not really the case is the recombination. So the transitions that produce light, and this changes things significantly in terms of constructing light emitters, and this is what we will discuss now. So let's talk about LEDs. These devices that you will probably have seen all around, come in different colors. They are very useful. They are extremely efficient. They convert above 90% of the electrical power that they receive into light. So they are really good devices that have changed the way we light up things, and we can now even find white LEDs, which is not strictly speaking true. The LEDs will have to be monochromatic, and we will give arguments for that in just a minute. But these devices are essentially just diodes that are made of the correct material. Okay, let's see. So LEDs are basically diodes, and we've already spoken about diodes. The only thing is these diodes are made of a material that has a direct bandgap. And what happens is, as you know already, when we have a depletion region, a little misalignment of the bands happens across the position of the joint, or in the vicinity of the joint. So in this side, that is the N side, you have excess of electrons. In the other side, which is the P side, you have excess of holes. And in principle, you have this region around, so that if the joint is somewhere around there, you will have this region roughly of the order of 1 micron thick, in which you have no carriers whatsoever. When the diode is biased directly, so that means when we put a negative pole on this side and a positive pole on this side, these basically repel the electrons and the holes into the conduction band. They actually produce a potential that then realigns and eventually misaligns the bands in the opposite direction. So what we have in the biased case is that that the bands, when they are biased, look like that. So what we have is electrons here that are pushed into the depletion region, holes there that are also pushed into the depletion region, and what happens is that these electrons here now that are spatially in the same position, so they are occupying the same physical space, but also, since we're assuming that this semiconductor is a direct bandgap semiconductor, these electrons can recombine here through the emission of a photon. Okay, and this means that these diodes will actually start emitting light, and yeah, that's the way these diodes operate. The energy of the if I draw the band structure in K-space, what we have is that we will have electrons over here. So these states will be populated, at least the bottom of the conduction band, in the region of the depletion zone, and also there will be a series of holes that are also electrically injected and which will tend to occupy the highest state. So the electrons will try to lower their energy as much as possible within the band, the holes will try to increase, well, to lower their energy, but increase their position in the band. And this means that now at least transitions here in the vicinity of the band gap will occur. So these transitions will start occurring. For the same arguments that we gave in the previous slide, these will produce photons, but very likely, I mean, if we have electrons here and holes here in positions away from the gamma point, so the zero momentum point, these ones will, if the states over here are unoccupied, and they should be because these transitions are occurring. So as soon as an electron reaches the bottom of the band, since there are holes to receive it, it will start recombining. So the states over here will be becoming free and free all the time. So these electron and these hole will, of course, they have the possibility of recombining, but they also have the possibility of thermalizing, so of trying to move first towards the minimum energy position in the conduction band. So really, most or almost all the optical transitions will occur here near the bottom of the band. So right at the band gap, and not happen with energies higher than the band gap, not typically at least. So in this sense, the wavelength or the energy of the photons that are emitted by these LEDs, although not perfectly monochromatic, it will be reasonably monochromatic. So LEDs can only emit, let's say, a single wavelength or a single band of wavelengths, but not all the colors that in principle are allowed. I mean, if you have a continuous band, all of these transitions between all of these states are in principle possible. However, only the ones that happen really close to the band edges will actually occur. And therefore, we expect LEDs to be reasonably monochromatic. Right, now that we have said that, this opens up a question: how do white LEDs work? And why are there LEDs with different colors? And well, the answer to that is relatively simple. It depends on the color depends on the semiconductor they're made of. So, for example, for infrared or really close to the red LEDs, you can use gallium arsenide. Gallium arsenide is a semiconductor that has a band gap of approximately 1.42 electron volts, which is somewhere in the infrared, 800 and something, or close to 900 nanometers. You can use indium phosphide, for example. Indium phosphide. You can use gallium nitride, which emits in the blue and the near so right at the edge between the blue and the violet and the ultraviolet. And by doing some alloys there and some tricks, you can push it down to the blue, and so on and so forth. All of these materials, or most of these materials, are materials that are 3-5 semiconductors. There are some alternatives as well. Instead of using 3 5s, you could use 2 4s. Sorry, 2 6. So materials that combine atoms from the group number 2 and from the group number 6, and that gets a little bit more complicated. But the group 2 materials have not just one electron missing, but 2, so they contribute with 2 holes, so to speak. And the numbers group 6 materials contribute 2 electrons, so they more or less balance out, and they also produce semiconductors that, like zinc telluride, for example. Zinc telluride which in principle can be used to emit green. Green is a particularly complicated region, and so on. So by picking the correct semiconductors, we can have maybe not any color, but a good collection of colors. But white light is, on the other hand, a color that is not a particular wavelength. It's the mixture of many wavelengths. So that how do white LEDs work? And white LEDs are every day more common in lighting. And the way they work, they are actually gallium nitride blue LEDs. So they are this type of LEDs. They are coated with a material that absorbs blue photons and then re-emits in many colors. So in a sense, a white LED is really a blue LED with a fluorescent coating. Talking about generally more, I mean, if we only have a finite series of 3-5 semiconductors, so gallium arsenide, indium phosphide, gallium nitride, and there are a few more, aluminum arsenide, which has a broader band gap, and so on. We would be limited just to a collection of different colors, and that would be it. So the question is, can we do better than that? And the answer is yes. There are what we call alloy semiconductors, and there are many types of many alloys or many combinations of materials in which we can produce other semiconductors that are not just one group 5 atom and one group 3 atom, or one group 2 and one group 6, for example, but a collection that is broader and that allows us picking many bandgap energies and therefore wavelengths to be used. So the materials that are the combination of two, for example, gallium arsenide, are called binary materials because they are formed by two atoms, by the combination of two atoms in equal amounts. However, one can make what is called ternary atoms, and they are things that are denoted like this. So, for example, aluminium, and I put an X there, gallium 1 minus X arsenide. And this looks like a strange chemical formula. So chemical formulas are usually, they have integer numbers. So you have one aluminium atom and 3 gallium atoms and arsenic or whatever, but they are usually integer numbers. And this X number is actually a fraction. It's a fraction that goes between 0 and 1. And what we observe here is that we are now creating a ternary lattice. So it's a lattice that combines arsenic. Half of the atoms are arsenic. And then we can put certain amount of aluminium and certain amount of gallium. And depending on the combination, we obtain different semiconductors with different properties. So with these, we have continuum. We can put, for example, 0% aluminium and 100% gallium, and that's gallium arsenide. But we could put, I don't know, 2% aluminium and 98% gallium, and that will give us a slightly different semiconductor. And if we put 50 in 50, that will give us another semiconductor, and so on. So just for you to have an idea, the band gap, so the separation between these the minimum of the conduction band and the maximum of the valence band behaves like this, as a function of the alloy fraction. So if we put here the alloy fraction, this is not the position, this is not X, the position is this alloy fraction. So is how many atoms of aluminium and gallium we put, or what's the fraction that we put. And what we obtain is that, let's make this plot very quickly, 0.1, 0.2, 0.3, 0.4, 0.5, and this is 1, so this is 0.1, 0.2, 0.3, 0.4, 0.5, and this is the band gap, energy in electron volts. So I would put 1.5, 1.6, 7, 8, 9, and 2. So this is 2, 1.4, and so on, right? And basically what we get is that at zero alloy fraction, we know this is gallium arsenide, so this is around 1.4 or so. Sorry, this is not 4, this is 6. 1.4 would be here, okay? So we start somewhere around there at zero alloy fraction, and as the alloy fraction increases, the band gap increases, and it increases up to more or less here. And I will draw the curve right there. So it does something that looks a little bit like that. And what this says is that as I increase the amount of aluminium atoms, the band gap starts getting bigger and bigger. So I will draw again a band structure here. What I'm drawing is the distance. So this band gap that I'm drawing over here is this band gap. So as I increase the amount of aluminium atoms and decrease the amount of gallium atoms, what happens is that these bands start separating from each other, until at some point somewhere in an alloy fraction around 0.45 or so, then something strange happens. In these, so the bands start separating, and at some point around that concentration that I set there, then the bands keep separating, but they also start misaligning. So at this point, at 0.45 or so, the material is no longer a direct bandgap semiconductor, and we're not really interested anymore. So we can use this in this fashion. So this opens the possibility of creating semiconductors that have a band gap that is tunable, that you can pick, you can choose energies in this region, and so 1.55 or so, somewhere around here, just for reference, is where the red color starts. So below there is infrared. You can hardly see it. Sometimes you can perceive it when it's very dark. But from 1.5 or so, a little bit above 1.5, then you start seeing red, and the more you start increasing, you go towards the yellow and so on, and you can produce LEDs with this type of semiconductor, in which you can choose a wavelength in this region. However, this is not the only ternary combination. There are many. I will just give you one extra one as an example. So, for example, we can also alloy the other side. So one can alloy the metal or the non-metal in the combination. So one can have, for example, gallium arsenic 1 minus X, antimonium X. So now we will change the other element. So now we will reduce the amount of arsenic, for example, from gallium arsenide. Again, when X equals 0, we start in gallium arsenide. These are just examples. There are many other alloys that can be made. If we make the band gap as function of the alloy fraction, so this is the alloy fraction and the band gap. In this case, what we obtain is more or less the opposite. Now with the alloy fraction, the band gap goes down from 1.5, 1.5, 1.4, 1.3, 1.2, 1.1 or so, and we will leave 1 over here. So 1.1, 1.2, 1.3, 1.4, 4, and 1.5, and we will put 0.1, 0.2, 0.3, 0.1, 0.2, 0.3. And in this case, what happens is that we start appearing in 1.42, which is gallium arsenide, and as we start increasing the alloy fraction, now the band gap starts going down, and somewhere around here between 0.2 and 0.3, the semiconductor stops being direct band gap, and this is somewhere there in between 1 and 1.1 electron volts in band gap. So once again, this allows us now going towards the infrared, so we can now tune the wavelength down to somewhere below 900 nanometers, so really well in the infrared, and going towards the telecommunication band at 1.5 microns wavelength. Okay, so again, this is just a series of semiconductors, alloys, and again, at this point here, it stops being a direct bandgap semiconductor, so we're not interested on it anymore, at least not for its optical emission properties. But these gives us handles that we can use to create semiconductors for different applications. If we want to use them for infrared telecommunications, or if we want to use them to illuminate a room, or to project colors on something, or to make LED TVs, for example. One can make red, green, and blue combinations of LEDs and drive them separately and so on to create pixels in a screen. And that's the way many commercial screens work, not all of them, of course. So yeah, that's it. And I just, before we finish this particular session, I want to give you one additional example of the types of things that one can do with semiconductors. And let's not worry too much about how to make this structure that I will tell you about in just a second, but let me just say that we can make them. In a session or two, we will discuss how to actually fabricate them. So let's assume that one can create layers of semiconductors, and one can deposit one after the other, and one can choose, for example, the composition of these layers. So let's say we have a wafer or a piece of semiconductor. So let's say we have a piece of semiconductor here, and we start depositing additional atoms on this surface, and create, let's say, a layer with this composition, and then we will create a layer with this composition. Okay? So what happens is we will have now a layer that we can create with this composition, and then we can create another layer, let's say a thicker layer, with this other composition. And let's assume that the original semiconductor, that the wafer, was originally as well of the yellow type, just for the sake of the argument. This means that as we move along this direction, and let's call this direction y, just not to confuse it with the x layer, that is the alloy fraction. So as we move over y, the question is, how do the bands look like? And the answer is, they will look something like this. If we put the conduction band, or the edge of the conduction band, we will have that. Then the edge of the valence band will be like that. And in this region in the middle, so in the red zone, this will have here an area where the band gap is actually smaller, right? So the bands will look like this now. Okay, so the band gap will get narrower in that bit. And let's redraw this again. So this is the yellow part, this is the yellow part, the first yellow part, the second yellow part. And in the thin layer that we sandwich there between the two yellow pieces of semiconductor, we have this thing. And if we now, again, this is positioned, so this is Y. And if we look into this here, and we just make it bigger. So I will just make a bigger drawing of what I'm circling there. We have is a series of states. These are states that are available, right? All of these states are available, or these states are available in principle. And what we have there is something that looks a lot like the square well. So what happens is that electrons that are in this region over here, so electrons that are populating the states here, that are essentially just a band. So it's a packed, very, very densely packed, almost continuum of levels in this region, will actually start feeling encapsulated. If they don't have enough energy to overcome the barrier, they will be confined to stay within this region. And this will produce additional quantization. So this continuum, or almost continuum of levels that are coming from the lattice potential, will be forced to be requantized. So now, instead of having a continuum of levels, we will maintain a continuum of levels over here in the top part, but here we will only have a series of allowed levels, which are basically the solution of the square well. So by choosing the size of the well, we can make now quantum engineering, and we can decide the spacing between these levels. So we can actually just by changing the thickness of this layer that we drew here, we can actually have control over where we put the quantum level. So this opens the possibility of doing quantum engineering, really making quantum systems that have the energy state that we want, not just the naturally occurring materials. So in principle, with these, we could create systems that have particular transitions and particular wavelengths and particular quantum properties that we impose by design. And this is one of those really super interesting things that are possible by using, for example, semiconductors and solids, and creating these types of quantum wells that do exist. They are not just a theoretical academic example. So with this, I want to finish this lecture on the optical properties of semiconductors, but we will discuss a few other devices in the next lectures. And we will also discuss now, in the coming lectures as well, a little bit about the fabrication of these types of devices. So thank you very much for listening, and I'll see you in the next session. Thank you very much.